All right, so we are in section 1.3 of Math 146. We're going to be talking about simplifying calculus expressions. These are things that are going to help you when eventually you do get to calculus, being able to simplify. And we're going to start off by talking a little bit more about factoring. Um, and we're not going to do a whole bunch of examples, but I'm going to give you some basic formulas for factoring that will help if you recognize them to make things a little bit easier in the factoring process. The first thing about factoring is you should always look for a common factor. If possible, the greatest common factor is the thing you should factor out first. It makes the problems a little bit easier because it usually lessens what you're looking at as far as, maybe the coefficients might be a little bit easier to deal with, or maybe the variables are going to be a little bit easier to deal with. So always look for a common factor first. So let's actually go ahead and write this down. So look for common factors. And if you can factor out common factors, you should do that first. After that, you have to kind of look at what kind of a problem you have. Do I have a binomial? Do I have a trinomial? Do I have a polynomial of 4 terms, 5 terms, whatever it is? Look to see what you have. There are some, like I said, there are some, let's just say, formulas that make this a little bit easier if you recognize them. If you have 2 terms, so if you have 2 terms, what you want to look at is, do I have a difference of squares? Difference of squares. So you do have to be able to recognize perfect squares in order to do this, but it makes things pretty simple. We've actually touched on one of these examples in a prior section when we did a factoring, but the idea basically is that if you have some kind of form of a squared minus b squared, to factor that, it will factor to a plus b, a minus b, the product of those two binomials. And that's probably the easiest thing to look at if you have 2 terms. Now, if you have the sum of squares, that does not factor, at least as far as real factors are concerned. Then you want to look to see if we've got trinomials, so 3 terms. This one has a bunch. Trinomials are probably the ones that we will factor most commonly, especially when solving equations. But you have what are called perfect square trinomials. Perfect square trinomials. This is going to be something that, if you recognize, makes things a little bit easier. And a perfect square trinomial basically takes on the form of a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. Notice that the a squared and the b squared in both of those are both positive, and that's because when you square any one of the terms, the a term or the b term, it's going to end up being positive. It just depends on whether one of those terms happens to be a negative as to whether you get that negative on the middle. And that's going to factor to either a plus b, the quantity squared, or a minus b, the quantity squared. So again, if you recognize something in those forms, it makes it a little bit easier to factor. If you don't have one of those special forms, and then you've just got a regular old trinomial, then you go with some other process, either again reversing the FOIL process or using a quadratic formula, which isn't really factoring, but it is a way to solve. Unlike, and I probably should have added this, we'll add it to the right hand side here, with two terms, you can have the difference or the sum of cubes. Difference or sum of cubes. So very much like the a squared minus b squared for the sum, for the difference of squares, you can have the difference of cubes. But you can also have the sum of cubes. This is one that works out for either one. And I wish I could tell you that there was some nice and easy way to figure these out. It's just kind of I mean, there are other methods, but this is just kind of a something to memorize. So if you have the difference or the sum of cubes, each one will start off with a binomial and will be multiplied by a trinomial in its factoring. The good thing is they pretty much factor the same way. There's just one small difference, and that has to do with the sign. So the difference of cubes is going to be the cube root of a, which goes here, and the cube root of b, which goes here. And since it's a difference, it gets a minus sign. And then for the trinomial portion, it is the a part squared. It is going to be the a times the b, but change the sign. So instead of being a times minus b, it's going to be a times a positive b. So it'll be plus ab. And then it is the b part squared. And then for the sum of cubes, it's pretty much identical. You've got an a here, you got a b here, and it's a plus in the middle because it's a sum. And the only thing that changes is, once again, you change that sign for the middle term. Otherwise, it's still a squared, but then it's minus ab, and then plus b squared. This one does not come up a lot, but it is good to know for when it does come up. And at the very least, it's something that you could look up if necessary when doing problems. Whether you need to know that for some kind of a test or quiz will be determined at a later point in time, and I would let you know if that is the case. So those are just a few basic formulas that you could use in order to factor. Again, anything else is just going to be standard factoring, and that is something that you should already kind of know at this point as far as factoring a trinomial. Factoring a trinomial, which is considered, factoring something which is considered prime, just means that it cannot be factored using standard methods of whole numbers, or integer coefficients, pretty much you can factor anything. And when it comes to this whole difference of cubes, difference of squares idea, obviously 25 is a perfect square. If you had 13, technically that's not a perfect square, but considering you can take the square root of it, technically it is a perfect square, but we don't deal with that. It's pretty much just, does it come out to be integers? That's what we're looking at there. All right. Whole bunch of methods of factoring. We already went through one in the prior section, factoring by grouping if you have 4 terms. So that's something to look for. Again, factoring, technically you can factor trinomials by grouping, by splitting up the middle term. I'm not really going to run through that process, but there is one for that. I think it makes things a little bit more lengthy, but again, if that's up to you, if you choose to want to do that. The more difficult ones are the trinomials, where you've got coefficients. Your a value is something other than 1, and that just makes things a little more challenging. But what I want to get to here, and I just want to touch on this real quick, is a process which is called completing the square. Completing the square. And it's kind of important for us to know some of these formulas that I just gave you, because that's literally what we're doing, is we're trying to get this down to a square. Specifically, we are trying to get to one of these 2 right here. So the idea is I want to get something into the form a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared, so that I can factor it down to what would be something over here, and these two are both what are considered squares. They're perfect squares because it's some quantity squared. So in order to complete the square, you have to basically look at what would be the middle term. For example, if I have, and this is just in general, if I have x squared plus 2ax plus a squared. Actually, that's a horrible example because it's already done. Let me see if I can give you an actual good example here. Let's say that we have the expression x squared plus 8x. And what we want to do is we want to create a perfect square trinomial out of this. So we can do that. Remember, the form has to be, since that's a plus in the middle, the form has to be a squared plus 2ab plus b squared. So what we're looking to do is we're looking to create that constant term here, that b squared on the end, which is going to complete the square so that we can factor this easily. So the process is pretty simple. You just look at this value right here. You look at the coefficient of the x, you're going to divide it in half, and then you're going to square it. So if we divide 8 in half, it's going to be 4, and then we square it. So we're going to add 16 onto that. What we have done now is completed the square, because if you factor that, that is now a perfect square trinomial. That would factor to x plus 4 times x plus 4, or x plus 4 squared. The problem, of course, is with this specific expression, we just can't arbitrarily add 16 to an expression. That changes the expression. But what you could do is add 16 to it like we did, but then subtract 16 from it also. Basically, now you're just adding 0. But by grouping this piece right here, that is completing the square, which now we could write as x plus 4 squared. And then don't forget, we still have to bring down that minus 16, because otherwise we change the expression. Now the expression is actually identical to what we started with, it just looks different. That's going to be something that can be used to solve specific types of problems in the future. So that's a good thing to know, how to complete the square. There are more complicated versions of this, especially if you happen to have a coefficient out in front of your x squared that's other than 1. And there's a little bit more work to do. We'll look at that if it ever comes up. But that is the basic idea behind completing square. And this completing the square, once again, is actually how the quadratic formula is derived. Like, that's how they actually do it. They complete the square. All right, I think that's probably enough as far as the review of the factoring stuff is concerned. Let's go ahead and move on to something else. So let's look at reducing rational expressions, simplifying rational expressions. And we're going to call it simplifying rational expressions because we are not solving for anything here. Eventually, this process can be used to help us solve for things, but we're not solving anything. There's no equal sign here. We are just simplifying expressions. So in basic ideas here, so let's, again, we are going to simplify expressions. So the basic idea here is if I gave you an expression like 2/4, at this point, we should definitely all know how to do that. That would reduce to 1/2. But the actual process that we're doing here would be, we are actually factoring that denominator to be the expression 2 times 2. And then what you can do, because everything here is some kind of a product or a quotient, in other words, everything's being multiplied or divided, we can actually divide the 2 on the top here with the 2 on the bottom here. A lot of people say canceling out. Technically what you're doing is dividing, because if you divide 2 by 2, you get 1, which is going to leave us with 1 divided by 2, or 1/2. Again, that's a definitely more mathematical way of thinking about it, but that's literally what you're doing. You can also think of it as dividing both the numerator and the denominator by 2, which is perfectly fine to do as well. Simplifying expressions is basically done in the same way, except now we're going to do this with more algebraic expressions. Specifically, we're going to talk about rational expressions, which are polynomials divided by polynomials. So this one will have a bunch of examples. Fair warning, this will probably be a 2-video lesson because the examples in this particular part are going to take some time, and then we've got a little bit more to do using radicals and exponent, excuse me, wow, I'm just having a hard time with the words here. Fractional exponents is what I was going for. All right, but in this case, let's do our first example. All right, example 1. All right, we want to reduce this to the lowest term. So we've got the expression x squared plus 4x plus 4 divided by x squared plus 3x plus 2. The idea is very similar to the whole 2/4 idea. What we want to do is we want to factor this stuff down into its simplest form. Right now, what we have are rational expressions, which consist of multiple terms being added or subtracted in the numerator and the denominator. Nothing can be divided out as it stands right now because they aren't factors. So we need to create factors. So in order to do that, let's factor the numerator. And if you recognize from what we did up top, that actually is one of our special cases, but we actually want to write this one out as multiple factors. This one factors to x plus 2 and x plus 2. The denominator is not one of your special ones. It's just a trinomial we have to factor. So you've got x and x. The only factors of 2 are 1 and 2. And since everything is positive, both of these things should be plus. And of course, you can always double check to make sure that that works by redistributing everything out, refoiling it out, but that one does work. So now what you should see is that I've got a factor of x plus 2 on the top and a factor of x plus 2 in the denominator, which will divide away. Both of those things will divide and give you a factor of 1. So that leaves us with x plus 2 divided by x plus 1, and that is simplified. That is in its most reduced form. Of course, what you would also have to notice here is that for this specific expression, should you be asked this question at some point, and this will come up, the domain or the set of x values that you can use include every x value except any x value that makes the denominator 0, and that goes from the original, not from the reduced form. So what you should look at is right here and right here, there are values in there that are going to make that denominator 0. The denominator would be made 0 by either x equals -1 or x equals -2. So this expression holds as long as x does not equal -1 or -2. And that has to do with your domain. All right, let's do another example. Example 2. Let's reduce. We're going to do a couple of different things here. Let's reduce x cubed minus 8 over x cubed minus 2x squared. And then we'll do another example very similar to this one. Okay, so x cubed minus 8 over x cubed minus 2x squared. Again, the idea is let's create factors. So x cubed minus 8. That is the difference of cubes. X cubed is a perfect cube, 8 is a perfect cube, and it is a minus sign. So we have to go back to our formula that we wrote down earlier. It's going to be a binomial times a trinomial. The binomial portion is the first, or the a value, which is x cubed, the cube root of that, that's x. The cube root of 8 is 2. and we keep the sign, which is a minus. The trinomial portion, we take that first term, that x, and square it. We multiply those two terms, the x and the negative 2 together, but change the sign. So now it'll become a plus 2x. And then we square that last term of 2 and get 4. So that numerator is factored. Once you factor that, by the way, unless you missed something else somewhere, that trinomial that's left over will not factor any further. In the denominator, let's see, I have two terms. I do not have a difference of perfect squares because the 2 is not a square and the x cubed is not a square. But I do have, and I should look for this all the time, a common factor. X squared is the greatest common factor, so I can factor out the x squared, which will leave an x minus 2, and that's a good thing because now we should see that we have a factor of x minus 2 in both the numerator and the denominator, which will divide out, and that will leave us with x squared excuse me, plus 2x plus 4, all divided by x squared. And once again, we have to look back at our domain. So that comes from the easiest terms right here are the factored terms. X cannot be 2 and x cannot be 0 because either one of the two of those would make your denominator 0. So this is going to be true such that x does not equal 2 or 0. All right, we can apply this same concept to multiplying and dividing rational expressions, which we're going to do with an example. Example 3, which is going to be x squared minus 2x plus 1 divided by x cubed plus x times 4x squared plus 4 divided by x squared plus x minus 2. So hopefully you remember multiplying fractions. You literally multiply across the top and across the bottom of the fractions, and that is how you multiply fractions. In this case, that would create an awful mess. It's not that it's wrong, but it would be much more difficult to simplify at the end because we are trying to simplify these expressions the best that we can. So in order to simplify, just like before, we want to go ahead and factor everything as much as possible. So let's go ahead and see what we can and cannot factor. We're going to treat this as basically 4 different pieces. I've got 2 numerators and 2 denominators. Let's look at the numerator of the leftmost term first. So that's going to be x squared minus 2x plus 1. Once again, that happens to be a perfect square trinomial, where each one of the pieces is going to be an x minus 1. Let's look at the denominator of that one. It's 2 terms. It looks like I definitely have an x in common, so we can factor an x out first, which would leave an x squared plus 1. Let's look at the numerator of the one on the right. Looks like the only thing I can factor out of that is a 4, because that would also leave an x squared plus 1, which hopefully you can see that's going to be a good thing. And then on the one on the bottom right, not a perfect square trinomial, so we just have to go to the idea of undoing the FOIL process. And that's going to be, it's going to be x and x. The only factors of 2 are 1 and 2. It's going to have to be a plus 2 and a minus 1 so that I get that plus x in the middle. All right, so here's the concept. Remember that I said when you multiply fractions together, you multiply across the top and across the bottom. So technically, when I do that, I'm going to have x minus 1 times 4 times x plus 1 all on the top. It's basically like just creating a longer fraction bar and saying, okay, all these things are now being multiplied together. So I can start canceling things out, dividing things out on the top and the bottom. And it doesn't matter which fraction it came from because it's multiplication. So the order of multiplication doesn't matter. So let's see, I've got an x squared plus 1 on the top here and on the bottom here. Those are going to divide out. I've got an x minus 1 on the top and on the bottom. Those are going to divide out. I don't have anything else that looks like it's going to divide out on the top and the bottom, so it looks like the most simplified form is 4 times x minus 1 over x times x plus 2. And once again, you kind of got to go back and figure out what your domain would have to be for all this stuff. Let's see, we've got a bunch of different pieces to consider. From right here, x can't be 0. From right here, x can't be 1. And from right here, x can't be negative 2. The x squared plus 1 right here doesn't give us any values that would make that would make the denominator 0. X squared plus 1 cannot be made 0 by any real number. Because if you think about it, no matter what you plug in for x, you're squaring it. So the smallest value that you could get there would be a 0 plus 1. So there's no way you can get a 0 out of that. So this would be the case, again, just as long as x does not equal, let's see, 0, 1, or negative 2. All right, let's try and do one by dividing. So we'll call this example 4. This one's always a little bit messier because dividing is much more, let's just say, vertically written, at least in the beginning. Looks worse than it is. This is what we call compound fractions. Fractions on top of fractions. Yay. Bunch of stuff we can do here. So the concept, again, just like you would do if you were dividing any regular, numerical fractions that are not have no variables in them. When you divide fractions, you're really multiplying the top fraction by the reciprocal of the bottom fraction. So we can rewrite this as x plus 3 over x squared minus 4 times the reciprocal of the bottom fraction, or basically take the bottom fraction and flip it over. And what that basically leaves us with now is the same type of problem that we just did. So we'll factor what we can. Fortunately, x plus 3 on the top of that first one is done. X squared minus 4, difference of squares. X minus 2x plus 2 times. We've got an x cubed minus 8. That is a difference of cubes. We've actually already done that one. We did it 2 problems. Oops, I forgot my cube. No, I didn't. Sorry, I'm looking at the wrong part of this thing as I go through it. So we've already done that. So it'll be x minus 2. And then x squared, multiply the 2 and change the sign. And then square the other one. And then the bottom part here is x squared minus x minus 12. So that'll be x. To get that minus 1 in the middle, we're going to need a 4 and a 3. Has to be a minus 4 and a plus 3. All right, so let's see what we can get rid of. We can get rid of the x plus 3. Oops, that's supposed to be in red. X plus 3 from there, x plus 3 from there. Got an x minus 2 I can get rid of there, and x minus 2 I can get rid of there. Looks like everything else stays. So we are going to end up with x squared plus 2x plus 4 divided by x plus 2, x minus 4. And nothing else can factor. So let's see. We have a bunch of things that we have to talk about here as far as 1, 2, 3, 4 values that x could not be because of domain issues. From here, x can't be 2, x can't be negative 2, x can't be 4, and x can't be negative 3. So x can't be 2, negative 2, 4, or negative 3. Because those would all give us domain issues right there. All right, multiplying and dividing is actually the easier ones to do. Adding and subtracting, not quite as easy. So this will be example 5. If we want to add or subtract, first thing you need to remember is when you add or subtract fractions, you must have a common denominator. Basically, you have the denominator tells you how many parts of the whole you have, and you can't add or subtract things that currently have different parts of the whole. So the easiest ones are things like 2x squared minus 4 over 2x plus 5 plus x plus 3 over 2x plus 5. And when I say that that's easier, it's easier because the denominators are already the same. So if that's the case, you just combine the numerators over top of the common denominator. So here you would get, let's see, that'll be 2x squared plus x, and then you can combine the negative 4 and the minus plus 3 and get minus 1 over 2x plus 5. And then assuming that that factors, you could always factor that numerator and see if it gets rid of anything with the 2x minus 5. In this case, I do not believe that it does, but we're going to factor it anyway because we want to put it in simplest form. So that'll have to be a 2x and an x. The only factors of 1 are 1 and 1. So in order to get that plus x in the middle, the 2 is going to have to be positive, which makes that 1 right there negative, over 2x plus 5. And the only denominator we have is 2x plus 5. So x can't be negative 5 halves. For domain issues. Right, that's what makes it a little bit easier is when you already have a common denominator. It's when you don't have a common denominator that we have stuff that we have to do. A couple different examples for that. So let's say that we have 2x over x minus 3, and we want to add that to 5 over 3 minus x. Now those denominators look very similar, but they aren't the same because x minus 3 is different than 3 minus x. But we can make them the same by doing a little bit of work. We can do a little bit of factoring. What these are is those denominators are what are called additive inverses of each other. The way I like to think of them is they are exactly the opposite. And if you have two things which are exactly the opposite, meaning every sign is different. So you have a positive x in one and negative x in the other, a positive 3 in one and negative 3 in the other. You can always factor out a negative 1 from one of them, and then it becomes the same. So we're going to write this as 2x over x minus 3. We're going to factor a negative 1 out of the bottom one. That's now going to make everything the 3 minus x the opposite signs, which makes it an x minus 3. And technically that negative 1 does not have to go in the denominator. It can go in the numerator. So we can basically move the negative 1 from the denominator up to the numerator and multiply it and make that a negative 5. So we'll have 2x over x minus 3 plus negative 5 over x minus 3. And now your denominators are the same, which now we can combine and get 2x minus 5 over x minus 3. And of course, x in this case could not be 3. I'm not writing that one down in this case because I kind of ran out of room over there, but x couldn't be 3 as far as a domain. So if you have things which are exactly the opposite, you can always factor a negative 1 out to make them the same. That's kind of an important concept. Now let's say that we have something which is slightly more a more common type of problem. Let's say that we have x minus 3 over x plus 4. We want to add that to x over x minus 2. The denominators there are not the same. They're not exactly the opposite of each other, so we can't use the concept of factoring out a negative. Remember, the idea behind finding a common denominator is you can always find a common denominator simply by multiplying your denominators together. Right? If you had 1/3 and you wanted to add it to 1/2, you would multiply the 2 and the 3 together and get 6 as a common denominator. It's the same concept here. We can find a common denominator by multiplying the denominators together. It's not always going to be the least common denominator, but in this case it will be, but you can find one. So in order to make a common denominator out of this, we want to multiply the fraction on the left by x minus 2. And we want to multiply the fraction on the right by x plus 4. But of course, you can't just multiply the denominators of a fraction because now you're changing the fraction. So we basically have to multiply the top by exactly the same thing that we multiplied on the bottom. Because ultimately now what you're doing is you're just multiplying each fraction by a factor of 1 in a different form. And that's okay because you can multiply anything by 1 and it doesn't change it. So now what we're going to get in the denominators are x minus 2 times x plus 4, and that's going to be that case for either one. And in the numerators, you're just going to go ahead and distribute everything out. So x minus 2 times x minus 3, that's going to basically be a FOIL problem, is x squared. We're going to get a minus 2x and a minus 3x, which is minus 5x, and plus 6. And then in the other one, it's just going to be x squared plus 4x. The denominators are now identical, so we can combine the numerators together. So we'll have x minus 2 and x plus 4. So adding our numerators together, we're going to get 2x squareds. So minus 15x and plus 4x is minus 11x, and then plus 6. And then the only other thing you want to do now is check to see, that isn't 11 by the way, no, it kind of looks like a 4. The only other thing you want to check for is, does this factor and eliminate any of our denominators? So let's go ahead and check just to see whether we can do that or not. I'm not sure that this is going to factor. And I know why it's not going to factor. Actually, this might factor the way I have it written, but I made a mistake, and hopefully you guys caught the mistake. That should not be a 15. I think I meant to write 5, and again, the pen, I apologize, the pen likes to drag anything that I'm doing. That's just supposed to be a 5x there, which is actually just going to give us a negative 1x here. Okay, and that actually does not factor. So that's it. X can't be 2, x can't be negative 4 from our denominators. So that's all we have there. So again, that's the concept of combining these fractions by getting a common denominator. All right, that's an awful lot to get to that point, and we haven't even gotten to the most important stuff yet, but we're going to come back with a second video which is going to continue this idea. We're going to we're going to simplify things by finding least common multiples. A lot of people think of those as least common denominators, except that it's the same idea, just without a fraction, and do a bunch of other problems.